Welcome to this first venture into podcasting from the BSN with the Journal of Neuroendocrinology. We're joining you from across many time zones between Australia, New Zealand and the UK to talk to you today about the upcoming special issue in J&E about insulin and insulin in the brain. So I'm Rebecca Dumbell, I'm the Communications Secretary for the BSN, and I'm joined today by the two guest editors for this special issue, Zane and Dave Grattan. So perhaps you both would like to introduce yourselves and tell us why you decided to do this special issue on insulin.
Thanks, Rebecca, and it's great to be here to talk to you today. Dave mentioned this late last year, doing this special issue because it was the 100-year anniversary since the discovery of insulin. And of course, we wanted to make sure that we highlighted the neuroendocrine roles of insulin. And that was really important for us. And we also wanted to take the opportunity to make sure that we could essentially use the journal as a way to promote neuroendocrine research on insulin.
I'm Dave Grattan from the University of Otago in New Zealand. Actually a former editor of the Journal of Neuroendocrinology, so it's a journal that's close to my heart. I got really excited by the story of insulin and the 100 years since the discovery of insulin was a nice landmark, but also I thought it was such a great story about how fundamental basic science led to the understanding of a biological process, which then led to the discovery of a hormone. And then, you know, within days, literally, of discovering the hormone, it was being used in a clinical setting and treating kids and essentially saving lives. And it's such a cool story that I thought it would make a great basis for a special issue. And so it's a real opportunity to highlight the neuroendocrine actions of insulin, as well as the whole story of the discovery of that hormone.
Perhaps you could tell us a little bit about the discovery of insulin and how that came about.
The disease diabetes had been known for hundreds, if not thousands of years, but the cause was unknown. And the basic researchers found that they could cause the disease by removing the pancreas from dogs. So all of a sudden there was this focus on what the hell is the pancreas doing to control blood glucose. And that was where Frederick Banting came in. And so he was then able to create a dog model and generate an extract of, a purified extract of endocrine secretion from the pancreas. And then they were using another dog model where they removed the pancreas and caused diabetes. And then they could treat that diabetes with the extract from the first dog. And so these basic experiments were essentially able to prove the idea that a hormone came from the pancreas and cured diabetes, and also provide a way to actually make a purified extract of that hormone. And it was literally months later that they were creating extracts from dogs and giving them to children who were suffering from diabetes, and essentially with a little bit of purification that came later in the story, they were able to generate an extract that would work and cured the disease. So it's a cool story of basic science leading to this discovery, and then immediate translation of that discovery into a treatment that worked.
I think that's really incredible, isn't it? And I think probably the only really modern day comparison that I can think of as something that works so quickly is the development of vaccines for COVID-19. So it's something that doesn't happen very often. So it must have been very exciting.
Well, I hope they didn't have the conspiracy theories back then.
Yes. they certainly had the controversy. If you read about it at the time, the hormone was apparently purified by 2 or 3 different groups, but it's Banting and Best who get the credit for it. You can go back and read, there's some great historical literature of the time about all of the other groups around the world that were doing similar things. But the credit goes to Banting and Best. And the really interesting thing is that, Banting was essentially a surgeon, and he was working in the labs of a guy called John McLeod. John McLeod was the expert scientist, but his name's not on the original paper. It's Banting and Best. Best was just the student who worked in the lab, essentially. But Banting and McLeod apparently fell out over the credit for what they were doing, and Banting didn't put McLeod's name on the original paper. but the Nobel Prize was awarded to the two of them. And so that was quite controversial as well, apparently. So it's a story full of human drama as well as the scientific discovery.
Originally, we didn't really think about insulin's actions in the brain. And certainly when you learn about insulin, maybe at high school or even at university, undergraduate level, you maybe are not really taught about what insulin does in the brain. So maybe you can tell us a little bit about why that is, why that kind of role has, or those roles have maybe been overlooked, and what we now know about the different functions of insulin in the brain.
After the discovery of insulin, where it was a miraculous cure, everybody wanted to understand how it worked, of course, and you could essentially take this extract, replace it, and you could essentially cure the diabetes. And of course, that is the ability to modulate blood glucose. And all of the initial work was looking at some of these peripheral organs that were sensitive, that could control blood glucose. So there was a lot of work done in the liver and the muscle and these sorts of tissues. And it wasn't until much later that people started thinking we should really be looking in the brain. And we actually have a great review by William Banks looking at the historical perspective on the interactions of insulin at the blood-brain barrier. So this is where people started to think insulin might be having an effect in the brain. And of course, because again of the important role of insulin in controlling blood glucose, a lot of that early work was how insulin acts in the brain to control blood glucose and also food intake. And we have a number of really important reviews that cover these important points on how insulin regulates glucose and energy homeostasis.
You did also mention that you've got some other articles in this special issue which cover other roles of insulin in the brain that maybe are not to do with metabolism or energy homeostasis. What did either of you find the most exciting areas that or maybe people wouldn't have thought about before they read this issue?
I guess this is a really important outcome of undertaking a task like this. You can actually see the breadth of the neuroendocrine functions of insulin. And so for me, I was really interested in the way in which insulin is now an important regulator of mood. For example, type 1 diabetes, type 2 diabetes is actually associated with anxiety and depression.
We treat diabetes as a disease of glucose homeostasis, and we're not really thinking about what else is insulin doing. So a lot of people with diabetes are being treated with drugs, including insulin, to maintain their blood glucose, with limited thought given to what else might insulin be doing in places like the brain, where it's not involved in glucose transport, or it's not involved directly in glucose homeostasis. So I think we really need to be aware of what these other functions are, so that we can manage the disease more appropriately.
And it's worthwhile saying that a number of people have labeled dementia as type 3 diabetes because of the lack of insulin action.
Maybe to finish up, I can ask you both what your main takeaway message is from putting together this special issue.
It's just the breadth of action of insulin in the brain. And that's reflected by the fact that insulin receptors are found throughout the brain in a number of different brain regions, where traditionally you wouldn't associate that with the control of blood glucose or appetite. So yeah, I'm really excited to see where we can go in the next 10 to 20 years in terms of understanding the insulin actions in the brain.
Yeah, for me, it comes back to that point that I made, as to why we even put this together at the beginning, and that's to recognize the value of understanding biology. And 100 years ago, it was the understanding of the basic hormonal regulation of glucose, the role of this hormone, and the fact that we could replace this hormone in people that don't have it. Now, we've got to the same sort of frontier of understanding the biology of what's going on with this hormone in the brain. Although we've got some great reviews in this issue explaining the state of the art in terms of our understanding, we've still got a long way to go to work out how it works. Over and over again, I just try to emphasize to anyone who will listen, when you understand biology, you have the power to influence or to use it. And that's what I see. This whole story is a great example of that to me. One of the other things I'd really like to give a bit of a plug for is the quality of the illustrations in the review. The Journal of Neuroendocrinology really stepped up and helped out the authors by providing professional assistance in creating their figures. So many of the reviews have really beautiful, really clear, descriptive figures to go with them. And so people will find them a great resource, I think, for teaching and other purposes. So take a look.
Brilliant. Well, thank you both for joining today and for telling us about this upcoming special issue in the Journal of Neuroendocrinology. I'm certainly really looking forward to reading all of these reviews. So thank you.
Thank you.
Thanks, Rebecca.